talk about vector, the definition. A quantity with magnitude and direction. It's some value, or it's maybe a shape.
Do you like vectors?
Generally. Some stuff gets really messy with them. So, some of it. Now when you're dealing with notation, you got several different forms. So first one like this. How is this different from the way you would do the notation for an array?
What?
How is this different from the notation for an array?
Array is just a one.
So array we use this. Whereas when talking about vectors, only half the array. And what this means,
An actual arrow.
and when you're doing an array, like you remember geometry, this is what we did. Whereas when we talk vector, we don't do a full arrow. What a vector does, it starts from one point, goes to another point in a direction. But the thing is, it doesn't necessarily have to be this positioning. No, we said it had magnitude and direction. We didn't say it had position. So if you were looking at it, let's pull up a graph. Here we have this vector, goes from here to there and stops.
Stop.
Yes.
Arrow.
To indicate the direction.
Absolutely.
So vectors have a set magnitude, a set length. They do not continue indefinitely, like rays do. But this vector right here is the exact same as that vector, which is the same as this vector. So if I copy these, so all these vectors are the exact same vector. Because they all have the same length and the same direction. So remember, the two things that a vector has is length, which is magnitude, and direction. Now, other notation that you may see is something like this, like a single lowercase letter, and other one is bold letter. Yes. So you might also, it's just a bold A, as I'm trying to do. So, typically when you see bold letters, we're talking about vectors. Now, oftentimes when we measure, remember we said they have magnitude and direction. We usually measure direction based on the standard position. So, standard positioning measures the angle from positive x-axis.
Positive?
Yeah.
Direct negative.
Correct. So, if it's a standard position, we're typically measuring this angle right here.
Oh, right.
Just like when we were dealing with trigonometry and stuff, we were measuring the angle starting from the positive x-axis. However, you may also see bearing used. The bearing is often used like if you're doing navigation. When we're talking about bearing, we're measuring from north. So, measured
Positive y.
from north, which is positive y-axis. And in this case, we go clockwise. So if we had this one, we'd be measuring this angle. So if it's in standard position, we get one measurement. We're measuring a bearing. So if it's talking about north, south, east, west, most likely you're dealing with bearing. Like if you were 15 degrees east of north. Here's something like that.
Yeah.
So 15 degrees east of north. So that would be something, this might be something like that. And with dealing with that, we're talking about comparison to true north, which is straight up.
What was your statement for the standard position one? Like, having a 15 degree north?
Well, if we just said 15, like if we were saying this is, as a bearing form, we say 15 degrees north of east. But and if you didn't say, if you just say 15 degrees, and we would assume we're using standard position. Unless it said a bearing of 15 degrees. So if it said a bearing of 15 degrees, we're talking from here, this direction, this.
Right.
So if I said a bearing of 170 degrees, we would be talking about this vector. Or we'd be going this direction. Whereas I just said 170 degrees, we'd be talking up here. So it depends on if we talk about bearing or if we're talking about direction. So if I say bearing or direction, we're talking about from true north.
So 15
See, this is that'd be one way of describing this direction. Well, it's east to the right of north. North is straight up. So what causes vectors to be equivalent?
same line direction.
Yeah. So equivalent, or I should say, vectors are equivalent if and only if they have the same magnitude and direction.
Magnitude of what?
Yeah.
What does it do with speed?
Well, velocity is a vector because we're going like 15 meters per second northward. So typically when you're talking about vectors, oftentimes it's applied to moving or to forces or to stuff like that. Okay, what about opposite vectors? What do you think that is?
Yeah, the same magnitude of opposite direction.
Or, yeah, opposite, if and only if they have same magnitude and opposite direction. Now, there's a special vector you need to be aware of. The zero vector. Oftentimes you're going to see it either bold zero or zero vector. I mean, I would usually write it like this. What is the length of a zero vector? Zero. What is the direction? Any direction.
It's just a point.
It's a vector that has zero magnitude.
What is that?
I guess you could say it that way. But it comes into play later. Read this chapter, but it's important. It has zero magnitude and can be considered going any direction we want it.
Is that the notation for it?
Yeah.
That's the only way to write it? Like, is there any other
Well, you
way
might
that-
also see it written as a bold zero. And typically you don't use O because it gets confused with zero. But oftentimes you don't use L except capital L or script L because you get confused with one. Depending on who's drawing it. Now, something you need to be able to do is combine these graphically.
My favorite.
So, graphically, no, adding. So let's say we're taking this vector and this vector, and we're going to add them.
Oh, this is the test that I like. I don't know.
So, the thing is, it's actually really easy to add them. Let's say we're doing that plus this. To get it, let's copy this one. So note on your book, you're going to have to do some tracing to be able to get equivalent vectors. Take that one, and let's copy this one. To do it, head to tail. And so our resulting vector, when we add them, is going to be this vector.
How do you write that in the notes?
Yes? Approximate. So, addition, relatively simple. How about subtraction? Let's copy everything here. Paste it. So this time, instead of adding, we're going to subtract. Yeah, the answer would be the blue one over here. It would be... What do you think subtraction would give? Any guess? So if we're taking this one minus this one.
Will the answer be the same?
What? The answer will not be the same.
You start with 5.
Okay. Well, we're taking this one minus this one.
Yeah.
What does subtraction typically mean? Going, when we talk about direction, what would subtraction mean? Going the opposite direction. Right? So what, with the easy way, you line up the head to head. And our vector would then be starting down here and going to the tail. The blue one would be the subtraction.
Wait, so how do you know which one?
Well, this is where we started.
Oh, so, like,
So you started with this one. No, with this first one, it doesn't matter the order because addition is commutative. So I could, for example, if I did this, if I did this one first, I did this one first up here, and then I added this one. Like I get the same answer either way.
how did you know which direction the one on?
It always starts at the same point as where you started at. So we started here, therefore that's the starting point of this.
Can we start with the shorter one?
We started here because we started right there. We're saying this one, we went this direction, and then we went this direction. For this one anyway, we went this direction, then we went down this direction. Here we went this way, except we went the opposite of that direction, which would be up here. Yes.
Are those two blue lines exactly the same?
No, they're not. They're going very different directions.
No.
No. Oh, maybe. But it doesn't look like they are.
Yeah. Did you show me?
No, I didn't. Oh, no, yes, I changed it around. So it wasn't copy and paste.
How do
They
you,
are.
how do you know how to accurately line up the head goes to the error?
Typically you're going to have you'd have a point here or something to help you line up. I mean, you're doing a book, you're basically going to be tracing.
How do you want the answers to show?
Well, I want you to see you doing the different parts. Like this
No,
would be,
it'll look like that.
yeah.
You want it to like have the.
You don't necessarily, you can show this part, you don't necessarily have to show that. Because, like in the book, it's going to give you two vectors and say, guess the addition of these two. And so the easiest thing is to trace it in your book.
So I can just leave it like then you'll know the.
Well, you have to make sure which one, it's clear which one is your addition. So for example, if we could each call this one vector u and this one vector v, and this would be u plus v. If you want to label it like that, or you put something to indicate that it is your answer.
And there's different colors.
Yeah. But we need something to indicate that this is different from the other two. So we can tell which one is actually your answer. Okay. Now we've got one more part. Scalar multiplication. Okay, what's a scalar? So when you just in matrices, it's the number you multiply out front of the matrix. It's a scalar. And we're applying the same thing. A scalar is just a numeric value. It does not have a direction. It's just, say we're multiplying a vector by 3. So, for example, let's say this is vector m is this vector right here. If I wanted to have 3 times vector m, what do? Yeah, so I'm going to copy this. 1, 2. So I start here. And get this lined up. And 3. My resultant would be all the math together. There. So my resultant would be this vector. Now, second section got to is easier than the first section because here we're doing it all graphically. Second section we're going to put adding the numbers in there to make it easier. But for now, graphically is what you've got.